Hello, this presentation addresses the determination of effective length of columns using alignment charts. Building upon earlier lectures which addressed Euler buckling of columns and the basis of the flexural buckling provisions included in the AISC specification, the idea of an effective length factor is described in more detail, and a procedure is introduced to determine the effective length factor for columns in various types of steel frames. Up to this point in our discussion of columns, we have taken the effective length, KL, as a given quantity. Typically, the length L is actually a given quantity that can be determined based on the structural layout that's being considered. However, the effective length factor, K, requires more discussion. Section 2 of AISC Chapter E says that the effective length, KL, shall be determined in accordance with Chapter C or Appendix 7. With this statement, AISC by reference provides several different methods for determining the effective length of a column, ranging from the simple idealizations that we have in Table C-A-7.1 to other, more complex buckling solutions that are specific to the frames and loading conditions that are encountered. In some types of frames, effective length factors are easily estimated, but in other cases, their determination is less obvious. So what do we do in those cases? Chapter C is titled Design for Stability. It's one of the more involved chapters that's included in the specification, and it's also one of the newer chapters that's in the specification. We also have Appendix 7, which is titled Alternative Methods of Design for Stability, that provides two more methods for addressing effective length. The procedures included in Chapter C are often referred to as a direct analysis method, and Appendix 7 includes the effective length method and the first order analysis method, both of which center around the use of alignment charts. The direct analysis method is a procedure where you use a refined second order analysis that includes several destabilizing effects in the structure, including P big delta and P little delta effects, material nonlinearities, and other effects. The reward for conducting such a sophisticated analysis is that in the end, the effective length factor, K, can be taken as 1.0 for all members. Using the alignment charts is generally considered to be simpler, at least for small problems, but the direct analysis method is fundamentally a better approach. Even though the effective length factors are a bit dated and are included in an appendix to the specification instead of in the main body of the specification itself, they are still useful and provide a measure of the amount of restraint provided at the ends of columns, even if some engineers would argue that it's an imperfect measure. So we're going to introduce effective length factors now and then revisit the details of the other approaches later. We have addressed the idealized end conditions considering a pinned-pin column as the baseline in other cases like fixed-fixed, fixed-pinned, or fixed-free columns. But how would we handle a case like the one shown here in an actual building where we have beams framing into the column? The column isn't necessarily fixed-fixed, but it isn't necessarily pinned-to-pin either. So what would we do in this case? Should we take K equal to 0.5 or 0.65? Or maybe we should be more conservative and take K equal to 1. Or maybe take K as something larger. What about a case like the one shown here, where the beams are relatively stocky compared to the column that they are framing into? In this case, the beams likely provide a higher degree of rotational restraint at the column ends, and it might make sense to take K as 0.5 or 0.65. But what about the case shown here on the right, where the beams are relatively slender compared to the column that they are framing into? In this case, the beams probably provide less rotational restraint at the column ends, and it might make more sense to take K as 1.0. The takeaway from this slide is that the relative stiffness of the column being considered and the beams framing into its ends is an important consideration in the determination of the effective length factor for a column. The details of the connections between the beams and the columns are also important. The beam framing into this joint from the left is rigidly connected to the column and can therefore provide rotational restraint to the ends of the columns framing into the joint. The beam framing in from the right, however, is pin connected and thus provides no rotational restraint to the columns framing into the joint. Another aspect that's important is being able to identify which type of framing system that the column is a part of. This slide shows two framing systems, a brace frame on the left and a moment resisting frame on the right. The little black triangles on the right indicate that those are rigid joints between the beams and the columns, so that's a moment resisting frame on the right and a brace frame on the left. In this case, using a 2-story X bracing configuration. The fundamental difference between the two systems is that the brace frame is much stiffer in resisting lateral loads than the moment frame is. As a result, we say that the brace frame is side sway inhibited, but the moment frame is side sway uninhibited. Brace frames are just one example of side sway inhibited framing systems. Shear wall systems would also be considered side sway inhibited. In general, any framing system with a relatively high lateral stiffness can be considered to be side sway inhibited. Finally, here are the two alignment charts that are used to calculate the effective length factor K. The alignment chart shown on the left is for a side sway inhibited frame, and the chart shown on the right is for a side sway uninhibited frame, or a moment resisting frame. These charts are constructed such that the effective length factor K is determined as a function of two G factors, one for each end of the column. G is the ratio of the flexural stiffness of the columns to the flexural stiffness of the beams that are framing into any given joint. So we take G equal to the sum of EI over L for the columns divided by the sum of EI over L for the girders at each joint. And there's one value of G for each end of the column, G top and G bottom. Or if you refer back to the charts in the previous slide, they're shown as G sub A and G sub B. These are ratios of stiffness, so it's appropriate that they include the modulus of elasticity. But since the modulus is always the same for the beams and the columns, we typically show G as the sum of I over L for the columns divided by the sum of I over L for the girders at each joint. Conceptually, G is a measure of the amount of rotational restraint provided at each end of the column. The general approach is to calculate a G value for the top of the column and a G value for the bottom of the column. Then you would use one of the two alignment charts to pick a value of K that is used for design. Suppose that you were considering a column in a moment resisting frame where G at one end of the column was 1.5 and G at the other end of the column was 3.0. In this case, you would use a straight edge to construct a line between those 2 points on the alignment chart, and then you pick K that is used for the design of the column. So in this case, you would use a value of K equals 1.62. Admittedly, using a straight edge and a chart is a rather crude means of determining a factor that plays such a large role in the strength of a column. There are equations that can be used in place of the alignment charts, and they're shown here. The first two equations can be used if the values of G at both ends of the column are not the same, and the second two equations can be used if you have the same value of G at both ends of the column. It's important to keep in mind, however, that even though you can use these equations to calculate K with several digits of precision, since these equations are basically curve fits to the charts, the resulting value actually isn't any more accurate than would be provided by using a straight edge and the charts. One aspect that is very important to keep in mind is that the value of G is a measure of the relative rotational restraint that a beam imparts on the end of a column. As such, when calculating the stiffness of a beam framing into the end of a column, the type of connection that is used between the beam and the column must be considered. If the beam is pinned to the column, as is shown here on the right where the W16 by 67 frames in, then the stiffness of that beam is taken as 0. G for this joint would be based only on the stiffness of the W18 by 55 framing in from the left and the stiffness of the W14 by 53 framing in from below and from above the joint. In cases where the base of a column frames into the foundation, we have to consider the rotational restraint that the foundation imparts on the column. The stiffness of the foundation takes the place of the stiffness of the girders that would be framing in. So in the case of a pinned base plate, where there is no rotational restraint provided, we would use a value of 0 in the denominator, and you are left with some non-zero stiffness in the numerator divided by 0 stiffness in the denominator, which would give you a result of G equals infinity. In truth, the rotational restraint provided by the foundation isn't actually 0, so we typically use a value of G equals 10 to represent the amount of fixity provided at the base of a pinned column. In the case of a fixed column base, there would theoretically be an infinite amount of rotational restraint provided at the base of the column, so you would use infinity in the denominator when calculating G, which would theoretically result in G equals 0. However, it's nearly impossible to eliminate all rotation at the base of a column, so we typically use a value of G equals 1 to represent a fixed column base. It's probably obvious by now that there's a bit of judgment involved in determining what is a pinned column base and what is a fixed column base. This determination can have a non-trivial effect on the effective length factor that the column is ultimately designed for, and this is one of the limitations of using the alignment charts. Still, the two photos shown here illustrate what might be considered to be a pinned base on the left and a fixed base on the right. The pinned base is basically a relatively thin base plate that is likely to bend under moment, permitting rotation of the end of the column under a relatively small bending moment. In contrast, the fixed base on the right is detailed to resist end moments at the base of the column by way of using a thicker base plate, stiffened channels, and additional anchor rods. Yet another aspect to consider is that one must be cognizant of the axis about which column buckling is being investigated when determining which beam stiffnesses to use. Consider the three-dimensional rendering of the column shown on this slide. When considering strong axis buckling of the column, one would calculate G for the top of the column using these beams indicated here in red. In contrast, when one was considering G for weak axis buckling of the column, one would use the stiffnesses of the beams shown here in green. Now let's take a look at the alignment chart for a side sway inhibited or brace frame. What is the most conservative value of K for a column in a brace frame? Well, if we look at the center line of this chart, we can see that for a side sway inhibited or brace frame, that K varies between 0.5 and 1.0. As a result, most practicing engineers will generally just take K equal to 1.0 if the frame is braced in the direction for which column buckling is considered. In fact, if side sway is inhibited in the direction relative to buckling, then the connections are often pinned anyways, thus G would be equal to infinity at both ends, and the effective length factor would be equal to 1.0 anyways. However, there are times when rigid connections are used in conjunction with braced frame systems, and in those cases you are permitted to calculate G factors and use a value of K less than 1. Nonetheless, many engineers will simply take K equal to 1.0 when considering a column where side sway is inhibited, such as the case at a brace frame. Now let's consider the alignment chart for a moment resisting frame. What is the most conservative value of K in this case? Looking at the center line of this chart, we can see that the largest value of K is infinity. What is the least conservative value of K? Again, looking at the center line of the alignment chart, we can see that the smallest value of K is actually 1.0. This corresponds to the side sway column, which is KC of table C-A-7.1. Both ends are completely restrained against rotation, but the top of the column is permitted to translate relative to the bottom. Another important consideration is that when moment-resisting frames are used in a steel structure, it is often the situation that only some of the columns are included in the moment framing in any given direction. These columns are referred to as stability columns. The remaining columns are included only to resist gravity loads and are often framed with simple connections and are thus treated as pinned-pinned. These gravity columns actually have a destabilizing effect on the stability columns that are part of the moment-resisting frames, and thus these gravity columns are referred to as leaning columns since they lean on or rely on the stability of the other columns for their own stability. Leaning columns can actually cause the effective length factor for a stability column to be larger than what would be calculated using the procedures described in this presentation. This is an advanced topic, however, and will be addressed later. For now, if a column is pinned, simply take K equal to 1, regardless of whether it is in a brace frame or in a moment-resisting frame. So the general procedure for determining the effective length factors for a column are: if the column is pinned with respect to weak axis buckling, then simply take K sub y equal to 1.0. Alternatively, calculate G factors for the top and the bottom of the column with respect to weak axis buckling, and then use the alignment chart to determine K sub y. Then go on and determine the effective slenderness ratio with respect to weak axis buckling, and then determine the weak axis buckling strength. Next, if the column is pinned with respect to strong axis buckling, simply take K sub x equal to 1.0. Otherwise, calculate G values for the top and the bottom of the column with respect to strong axis buckling, and then use the alignment charts to determine K sub x. Finally, determine the effective slenderness ratio with respect to strong axis buckling, and then determine the strong axis buckling strength. There are several assumptions that were made during the derivation of the alignment charts. The most fundamental of those are shown here. Consider the first assumption, that the behavior of the frame is purely elastic. Is that always true? Well, there are two types of flexural buckling that we consider based on the value of the column's effective slenderness ratio. When the slenderness ratio is small, inelastic flexural buckling governs, and the word inelastic means that the behavior of the frame is not purely elastic. Thus, the first assumption is violated. So what do we do in those cases? When inelastic buckling governs the strength of a column, and when the alignment charts were used to determine the effective length factor, the calculated strength is actually somewhat conservative. This means that the strength of the column will actually be larger than the strength that was computed. Engineers are permitted to refine their calculations by incorporating a stiffness reduction factor, tau, into their calculations. This is done by computing modified G factors, G sub prime factors, that are used to compute a refined effective length factor, K prime, that is smaller than the original value. When the effective length factor is reduced, the slenderness ratio is reduced and the strength is increased. The stiffness reduction factor, tau, is a function of the ratio of the tangent modulus to the elastic modulus of the column. As we'll see later, calculating the tangent modulus E sub t is quite challenging, and thus this equation for tau isn't very useful. Instead, tau can be calculated using these equations shown here. When the column is lightly loaded, the stiffness reduction factor is taken as 1.0, which reflects the idea that the column remains fully elastic. When the column is not lightly loaded, when the ratio of P sub u over P sub y is greater than 0.5, then tau is calculated using the second equation here, which is a function of the ratio of P sub u over P sub y. In its most general form, the stiffness reduction factor will be different for each column that frames into a joint, but it's much simpler and not terribly inaccurate to take tau as constant at each joint. It should also be noted that the calculation of tau is slightly different if you're dealing with a column section that has slender elements. Note that there is a table in Chapter 4 of the AISC manual that provides a stiffness reduction factor, tau, as a function of the ratio of P sub u over P sub y and the nominal strength of the column. Remember that two criteria must be met in order to use the stiffness reduction factor. First, the column strength has to be governed by inelastic buckling, and second, the effective length factor must have been computed using the alignment charts. Also remember that using the stiffness reduction factor is optional. If you choose not to use the stiffness reduction factor, then the computed column strength will be slightly conservative. To implement the stiffness reduction factor, first compute the stiffness ratios G for the top and bottom of the column, then the effective length factor K, and then the design resistance phi times P sub n. Next, if you find that inelastic buckling governs, you are permitted to compute the stiffness reduction factor, then modified values of the stiffness ratios, G prime, and then a modified effective length factor, K prime. Finally, you can compute a refined value of phi times P sub n based on the modified effective length factor, K prime. It is also worth noting that in its most fundamental form, with tau equal to the ratio of the tangent modulus to the elastic modulus, the process for finding the refined strength is actually iterative. The equations shown in this presentation and in AISC Table 4-13 are slightly simplified to make the process deterministic. Let's revisit the assumptions that went into the derivation of the alignment charts. We've just addressed the first assumption that the behavior of the column is purely elastic. The second assumption is that all members have a constant cross-section. That's a pretty good assumption for most steel frame building type construction, with the exception of light metal buildings where it's not uncommon to see tapered or non-prismatic members. The third assumption is that all joints are fully restrained. That means that there's a moment connection between the ends of every beam and every column, And we briefly addressed this earlier in the slideshow, but this assumption is clearly violated with some regularity, so let's take a closer look at this now. As we stated earlier, when a beam is pinned to a column, then the stiffness of that beam is taken as 0 when calculating the stiffness ratio G for that joint. However, what happens when we encounter a beam that is rigidly connected to a column under consideration but is not rigidly connected at the opposite end? The approach for handling this situation is different depending on whether the frame is braced or unbraced. For unbraced frames, the approach is to use a modified length, L sub G prime, to determine the stiffness of the girder. The equation for L sub G prime is based on the ratio of the moment at the far end, M sub F, to the moment at the near end, M sub N. The ratio of M sub F to M sub N is taken as positive if the girder is in double curvature, like it would be under a lateral load, and is taken as negative if the girder is in single curvature, as it would be under gravity load. The definition of near and far is relative to the column that is being considered. For example, consider the joint in the center of the hypothetical frame shown here. The near end of girder 1 is its right end, and the far end of girder 1 is its left end. On the other hand, the near end of girder 2 is the left end, and the far end of girder 2 is its right end. So if the near end of the girder is pinned, in other words, if the girder is pin connected to the column that's being considered, then the moment at that end of the girder, M sub N, is by definition 0. If M sub N is 0, then the ratio of M sub F to M sub N is equal to infinity, regardless of what the moment is at the far end. Thus, the modified length of the girder, L sub G prime, is equal to infinity, and the contribution of EI over L for that girder to the stiffness of the joint is equal to 0. This mathematically validates what was stated earlier, that when a beam or a girder is pin connected to a column, the stiffness of that beam or girder is taken as 0 when calculating G. If both ends of the girder are rigidly connected, as is shown here for girder 1, then the ratio of M sub F to M sub N is equal to 1. The modified girder length L sub G prime is equal to its actual length L sub G, and the stiffness contribution EI over L is taken at face value. On the other hand, if the near end of the girder is rigidly connected but the far end is pinned, as is shown for girder 2 here, then the moment at the far end of the girder, M sub F, is by definition 0, and then the modified length of the girder, L sub G prime, is equal to twice the actual length. In that case, we would take half the stiffness contribution, EI over L, of the girder when calculating the stiffness ratio of the joint, G. Finally, consider the case here where the far end of the girder is completely restrained against rotation. This is a bit different than a rigid joint in that with a rigid joint, the end of the beam rotates by the same amount as the column that it's attached to. In this case, however, the end of the beam is completely restrained against rotation, as if it were cast into a large block of concrete. We use the word incastra to describe this situation, and in this case, the modified girder length L sub G prime is equal to 1.5 times the actual girder length L sub G. And the stiffness contribution of the girder to the joint is taken as 2/3 of its face value when evaluating the stiffness ratio G. However, this situation is encountered much less frequently than other cases. For the sake of clarity, consider the definitions that are shown here. Pinned is taken to mean that the end of a beam rotates independently from the column that it is attached to. Fixed is taken to mean that the end of the beam rotates by the same amount as the column that it's attached to, and incastra is taken to mean that there is no rotation at the end of the beam whatsoever. A restrained joint is thus considered to be a fixed within this context, and a fixed column base is considered to be incastra within this context. The approach for handling non-rigid joints in brace frames is much simpler than it is in moment frames. As is the situation in every case, when the near end of a girder is pinned to the column, then the stiffness of that girder is neglected in the calculation of the joint stiffness ratio G. If the near end of the girder in a brace frame is rigidly connected and the far end of the girder is pin connected, then you multiply the girder's stiffness contribution by a factor of 1.5 in the calculation of the stiffness ratio for the joint, G. Finally, If the near end of the girder in a brace frame is rigidly connected and the far end of the girder is in castra, then you multiply the girder's stiffness contribution by a factor of 2 in the calculation of the joint stiffness ratio G. In closing, I should mention that this discussion is really just the tip of the iceberg with respect to column and frame stability. Effective length factors are being phased out as the direct analysis method is being more broadly adopted. If we use the direct analysis method, we can take the effective length factors as 1.0 for every member in the frame as long as we account for member and connection deformations, P big delta and P little delta effects, geometric imperfections, stiffness reductions due to inelasticity, and other uncertainties. I expect that within the next 10 to 20 years that effective length factors will likely be eliminated from the specification entirely in deference to the adoption of the direct analysis method for all frames.